need the fresh sheet here. And oh, this is what I need, never mind. So in the last couple videos, we talked about negative exponents. Then we talked about this situation here. So if the amount is principal times the quantity 1 plus I to the n, you can rearrange. So P is A divided by 1 plus I all to the n, or A times 1 plus I to the negative n. So we have that. And what if we wanted to use that to solve this problem? How much should you deposit in an account paying 6% compounded semi-annually, remember that's twice a year, in order to be able to withdraw $1,000 every 6 months for the next 3 years? So we're trying to work out how much money we have to invest up front if we want $1,000 laying around every 6 months for the next 3 years. And we're supposed to be at a point where after the last payment, there's no money left in the account. So one way to think of this is that we want to, if we can think about finding the present value of each $1,000 that's paid out during the 3 years, that's where we can use this formula. We can think of it as the value of each $1,000 is the amount times the quantity 1 plus I to the negative n. So let's look at this. We know that the periodic interest rate is 0.03, 6% per year, divided by 2 compounds per year. The present value P for the first payment is 1,000 amount times 1.03 to the minus 1, or 1,000 divided by 1.03. And then the present value of the second payment will be this, and this is what it looks like over time. So the first period we put in $1,000, and then that's the amount it grows by. And if you divide 1,000 by 1.03, you'll get something bigger. And then we're going to take 1,000 divided by 1.03 squared, or multiply by 1.03 to the negative second. So this should look an awful lot like when we derived the annuity formula in a previous video. And again, we don't want to add we don't want to do all these multiplications and then add. We'd really like to be able to do this in one fell swoop. So what we're going to do is we're going to call this P and say that, blast. Okay, fine. P equals 1,000, 1.03 to the minus 1, plus 1,000, 1.03 to the minus 2, 1,000, 1.03 to the minus 3, 1,000, 1.03 to the minus 4, plus 1,000, 1.03 to the minus 5, 1,000, 1.03 to the minus 6. Did I do that right? I did. Good for me. And notice that every single one of these terms, recall that a term is separated by addition. Every one of these terms has a factor of 1.03 to the minus some power. So definitely some factor of 1.03. So let's do what we did before and multiply through by 1.03p. Then we get 1,000. And then that's just going to be 1,000 because remember, as an aside, where's my thing? I'm so confused. There it is. 1.03 to the minus 1 times 1.03 to the positive 1 equals 1.03 to the 0, which equals 1. And we showed that in the negative exponents video. So if that's not clear to you, go back to the negative exponents video and watch that again. And if it's still not clear, let me know. So now that first term is just 1,000. Now 1.03, and we have a negative 2 times a positive 1, so that's just going to be a negative 1 here. 1,000, 1.03 to the negative 2, 1.03 to the negative 2 times 1.03 to the negative 1 is 1.03 to negative 2 divided by 1.03 to the positive 1, which is 1.03 to the negative 1. 1.03 to the fourth. Oh, 1.03 to the fifth. Sorry, it's kind of smudgy. Now, we subtract. As you know, subtraction makes a difference. 1.03p minus p equals, and look at all the lovely cancellations. That and that cancel. That and that cancel. That and that cancel. So do those. So do those. And we are left with 1,000 minus 1,000 times 1.03 to the negative sixth. And notice on this left-hand side, both of these terms have a factor of p. Remember, terms are separated by addition, and this is addition of the opposite of p. And this means 1p. So p times the quantity of 1.03 minus 1. Both of these terms have a factor of 1,000. 1 minus 1.03 to the negative sixth. P 1.03 minus 1 is 0.03. And dividing by 0.03, which you might recognize as the periodic interest rate, we get P equals 1,000, 1 minus 1 plus the periodic interest rate, raised to the opposite of the number of years over 0.03. And in general, we have P equals, and now let's go to the book because I want it to be consistent with the lettering they use. So we get P, in general, we get P equals R, where R is the oh no, we're going to use this present value equals future value. Rats. Payment, rather. 1 minus I to the minus n power, all divided by I. And then you can put these brackets here if you like to remind yourself. The order of operations also gives it to you. But that is where the present value of an ordinary annuity formula comes from. I hope that that was helpful.